Good morning, everyone, and welcome to today's presentation. I'm Dr. S.K. Singh, and I'm delighted to have you all here. Today, we'll be exploring the fascinating topic of chemical oxygen demand, or COD. This is a crucial parameter in water quality assessment and environmental monitoring. Over the course of this presentation, I'll guide you through what COD is, why it's important, and how we measure it. So let's get started and delve into this important subject together. Let's take a closer look at chemical oxygen demand, or COD. Essentially, COD measures how much oxygen is needed to chemically break down organic and certain inorganic compounds in a water sample. It's a way to quantify the total organic load. That is, all the stuff that can consume oxygen during treatment. When we talk about units, we're referring to milligrams of oxygen per liter of water, or mg/L. Now, why is this important? Well, COD is critical for environmental compliance and for assessing how effective wastewater treatment processes are. It's a key parameter regulators look at to ensure that effluents won't deplete dissolved oxygen in receiving waters, which is vital for protecting aquatic life. You'll find COD being used in discharge regulations, industrial wastewater monitoring, and in checking how well treatment plants are performing. Standards like ISO 6060 and many national norms specify how to test for COD and how to report the results. So, in summary, COD helps us understand the organic pollution level in water and ensures that our water bodies stay healthy and balanced. Let's take a closer look at how COD, or chemical oxygen demand, is different from BOD, biological oxygen demand. Both are important measures of water quality, but they actually evaluate different aspects of organic matter in water. BOD focuses on the amount of oxygen that microorganisms need to decompose organic material over a specific period, usually 5 days. It gives us a sense of how biodegradable the pollutants are. On the other hand, COD measures the total amount of oxygen required to chemically oxidize all organic substances in the water, including those that microbes can't easily break down. So, COD provides a quicker, more comprehensive snapshot of the total organic load, regardless of whether those substances are biodegradable. Understanding these differences helps us interpret water quality data more accurately and decide on the best treatment methods. It's a key part of our overall theme, assessing and managing water quality effectively. Today, I want to introduce you to the standard regulatory method, specifically ISO 6060, which is the internationally recognized standard for determining chemical oxygen demand, or COD, in water. This method is widely accepted not only by regulatory authorities, but also by laboratories around the world, ensuring consistency and reliability in water quality testing. The core principle of this method involves taking a water sample and subjecting it to a digestion process with an excess amount of potassium dichromate, or K2Cr2O7, in an acidic environment. During this process, the potassium dichromate acts as an oxidizing agent, reacting with the organic substances present in the water and consuming oxygen in the process. After the digestion, we need to determine how much of the oxidant remains unused. We do this by titrating the sample to quantify the unreacted potassium dichromate. The difference between the initial amount added and what remains after digestion gives us the amount of oxygen that was consumed during oxidation. This oxygen demand is a crucial indicator of the organic pollution level in water, and understanding this helps us assess water quality effectively and consistently across different testing environments. So, the ISO 6060 method provides a standardized, reliable way to measure water quality through chemical oxygen demand, connecting directly to our broader goal of ensuring safe and clean water. Now, let's take a closer look at the chemistry involved in this process, specifically oxidation and titration. When we perform this method, we use a set of reagents that are crucial for the reaction to proceed accurately. The main oxidant here is potassium dichromate, which is responsible for oxidizing the organic matter. Alongside that, we add concentrated sulfuric acid to create the right acidic environment for the reaction. We also include silver sulfate as a catalyst to facilitate the process, ensuring it happens efficiently. To prevent interference from chlorides, we add mercuric sulfate, which helps reduce any potential complications. For the titration, we use a standard solution of ferrous ammonium sulfate, or FAS, which acts as our titrant to quantify the unreacted dichromate. And to signal the endpoint of the titration, we employ a ferrine indicator, which changes color when the reaction is complete. The overall reaction involves the organic matter reacting with dichromate, producing oxidized products and Cr3 ions, which are reduced in the process. Any remaining, unreacted dichromate is then measured by titrating it with FAS. This step is key because it allows us to determine the amount of organic matter present based on how much dichromate has been consumed. This method is a classic example of how oxidation and titration work together to analyze complex samples accurately. Now let's discuss the closed reflux procedure. First, we start with sample preparation, where we measure a fixed volume, typically between 10 to 50 milliliters. This ensures consistency across our tests. Next, we prepare our oxidation mix by adding potassium dichromate, sulfuric acid, and any necessary catalysts. These reagents are crucial for the oxidation process. Then, we proceed to reflux digestion. We heat the mixture in a reflux apparatus at a controlled temperature, around 148 to 150 degrees Celsius, for about 2 hours. This step allows the oxidation to occur thoroughly while preventing loss of volatile components. After digestion, we cool the mixture and move on to titration. Here, we titrate the remaining dichromate with FAS, or ferrous ammonium sulfate, using a ferrine indicator to signal the endpoint. It's also important to run a blank test in parallel, using distilled water instead of the sample. This helps us account for any background reagent effects, ensuring our results are accurate and reliable. Overall, this procedure is a key part of our analytical process, allowing us to accurately determine the sample's content through controlled oxidation and titration. Now, let's talk about regulatory controls and quality checks. Ensuring method validity is a key part of this, and it involves several important expectations. First, laboratories must use calibrated glassware and reagents. This helps ensure that measurements are accurate and reliable. Next, it's essential to include blanks and standards in every batch. This way, we can verify the accuracy of our methods and detect any contamination or errors. Sample preservation until analysis is another critical point. This ensures that the samples remain unchanged and representative of the original material. Additionally, documenting any deviations and the conditions under which analyses are performed is vital. This documentation provides transparency and traceability, which are essential for quality assurance. For laboratories aiming for accreditation, like ISO IEC 17025, demonstrating method precision and accuracy isn't optional. They need to show consistent, reliable results over time. All these controls and checks are fundamental to maintaining high standards and ensuring the integrity of our testing processes, which ties back to the overall theme of quality and regulatory compliance in our work. Let's take a closer look at the COD calculation formula. The standard method for measuring chemical oxygen demand using titrometric analysis involves this equation. COD in milligrams per liter is equal to the difference between the blank titrant volume and the sample titrant volume, multiplied by the normality of the titrant, and then scaled by a factor of 8,000. Now, that 8,000 might look a bit intimidating, but it actually combines important conversion factors. It accounts for the molecular weight of oxygen, which is 8 grams per mole, and it converts liters to milliliters. Breaking down the variables, VB is the volume in milliliters of titrant used for the blank, which helps us account for any reagents or impurities. Vs is the volume of titrant used for the actual sample. N is the normality of the FAS titrant, which tells us how reactive it is. And finally, Vs is the volume of the sample itself, also in milliliters. By plugging these values into the formula, we can accurately determine the amount of oxygen demand in the sample, which is crucial for assessing water quality. This formula ties back to our overall theme of understanding how to measure and interpret water contaminants effectively. All right, let's walk through an example calculation to understand how we determine the chemical oxygen demand, or COD, of a sample. First, we start with the given values. The bod volume, VB, which is 25.6 ml, and the sample volume, Vs, which is 23.8 ml. We also have the normality, N, which is 0.025 N. The calculation involves subtracting the sample volume from the bod volume. So, 25.6 minus 23.8. This gives us the difference in milliliters. Next, we multiply that difference by the normality, 0.025 N, and then by 8,000, which is a conversion factor to get to mg/L. Finally, we divide the whole product by the volume of the sample, which is 10 ml in this case. Putting it all together, the calculation looks like this: 1.8 times 0.025 times 8,000 divided by 10. Doing the math, that results in 360 divided by 10, which equals 36 mg per liter. So, the chemical oxygen demand of this sample is 36 mg O2 per liter. This example really highlights how we quantify organic pollution in water samples, which ties into our overall theme of assessing water quality. Now, let's look at some practical interpretations of COD levels. When the COD is low, below 50 milligrams per liter, it typically indicates low organic pollution, such as treated effluent that's been properly processed. Moving to the moderate range, between 100 and 300 milligrams per liter, this is what you usually see in raw municipal wastewater, kind of the typical load we expect. And when the COD is over 500 milligrams per liter, that's a sign of industrial wastewater with a heavy organic load, which often requires more intensive treatment. These interpretations are essential because they help us optimize treatment processes and ensure compliance with regulatory standards. Now, let's talk about some common variations in the methods we use to measure COD. One popular method is the closed reflux colorimetric technique. Instead of titrating, this approach measures the remaining dichromate through spectrophotometry, making it faster and more suitable for routine screening. It's a great way to get quick results without sacrificing accuracy. Another method is the potassium permanganate approach. It's simpler and easier to perform, but provides a less complete oxidation, so it's mainly used for rough estimates rather than precise measurements. Now, handling samples properly is critical to getting accurate results. First, consider potential interferences. For example, chloride ions can interfere with the measurements, but adding mercuric sulfate can help reduce that interference. Suspended solids can pose problems too, so pre-treatment might be necessary to prevent turbidity from affecting the analysis. Lastly, proper sample preservation and prompt analysis are vital because delays or improper handling can alter the sample composition and lead to inaccurate results. All these points are interconnected and help us ensure that our COD measurements are reliable, which is essential for effective wastewater management and environmental protection. Let's talk about regulatory and environmental compliance. As you're likely aware, COD results are often a key requirement in environmental permits. These permits are crucial for ensuring that wastewater discharges meet regulatory standards. They also play a vital role in monitoring industrial effluents, helping us track and control pollutants released into the environment. Furthermore, the results from COD testing are essential for evaluating the performance of treatment plants. They provide valuable data to confirm that these facilities are functioning effectively and within legal limits. It's also important to understand that these results are frequently included in environmental impact assessments and regulatory filings. This means they are part of the documentation that demonstrates compliance and environmental responsibility. On a broader scale, standards like ISO 6060 serve as the global framework that regulators rely on. These standards ensure consistency, reliability, and comparability of results across different regions and industries. Overall, adhering to these compliance requirements not only helps protect the environment, but also supports sustainable operations and regulatory trust. Let's go over the key takeaways from this slide. First, COD stands for chemical oxygen demand, and it essentially measures the oxygen equivalent of the organic matter that can be oxidized in water. This gives us an important indicator of water quality and pollution levels. Next, we rely on standardized methods, like ISO 6060, which use strong oxidants, reflux steps, and titration techniques to determine the amount of oxidizable material. These methods are designed to be consistent and reliable. The calculations involved take the differences in titration results and convert them into milligrams per liter of oxygen demand. This conversion is crucial because it allows us to quantify pollution levels accurately. Finally, and perhaps most importantly, following proper procedures and maintaining quality control throughout the process is essential. This ensures that our results are both accurate and compliant with regulatory standards. All of these points tie back to our overall goal, accurately assessing water quality to protect public health and the environment. For further support, please don't hesitate to reach out. If you have any questions or need additional information, I'm here to help. Remember, we're committed to ensuring you have all the resources you need to succeed. Thank you so much for your time and attention today.